Our solar system represents an extensive and complex cosmic domain that did not appear spontaneously. Approximately 4,600,000,000 years ago, an enormous frozen cloud of interstellar gas and dust, a diffuse vestige of ancient supernovas and primordial material of the universe, originated our central star. A cosmic event of great magnitude, possibly the expansive shockwave of a nearby supernova, altered the tranquility of this nebula, causing its gradual collapse under the influence of its own gravitation. As the mass contracted, forming a rotating disk, the pressure and temperature at its center increased vertiginously. This intense compression finally triggered nuclear fusion, converting hydrogen into helium and initiating the birth of the Sun. Its luminosity, a fundamental force, pierced through the cosmic darkness, while its immense gravity exercised an irresistible attraction over all the surrounding material, thus marking the emergence of our solar system. This system does not constitute simply a grouping of celestial bodies, but an organized and dynamic domain, continuously molded by the omnipresent influence of the Sun. The sphere of solar dominion extends much further than what our vision can directly perceive. The true limit of our solar system does not present a clear demarcation, but rather represents the distant point where its dominant force vanishes into the vastness of space. Although solar gravity extends infinitely through the cosmos, it is its solar wind, a continuous stream of charged particles that generates an immense protective bubble called the Heliosphere, which envelops the entire system. This invisible shield extends approximately 11 billion kilometers from the Sun. In this frontier region, the solar wind collides with unfiltered radiation and dispersed matter of interstellar space, marking the last perceptible breath of solar influence. Beyond the heliosphere, the solar system progressively dissolves into the immense galactic framework. Solar attraction gradually weakens and its presence merges with the vast cosmic background. Nevertheless, within this immense volume, each component remains as an integral part of the solar system, a system defined not by its individual elements, but by the encompassing reach of its central star. This essentially constitutes our solar system, a realm of light, gravity, and movement, sculpted in the spatial immensity by the power of a single burning star. Let us begin our epic journey from the very epicenter of the system, its incandescent heart, the Sun, a colossal sphere of nuclear plasma, a cosmic engine that consumes its fuel with incessant energy. It is a millennial entity, powerful beyond comprehension and of absolute dominance, maintaining the solar system cohesive through an invisible gravitational force. The Sun possesses an estimated age of 4,600,000,000 years. Formed from the same primordial nebula of gas and dust that gave origin to all the surrounding celestial bodies, it is an incomparable giant in our cosmic system, constituting 99.8% of the total mass of our stellar neighborhood. If it were possible to gather the combined mass of each planet, moon, asteroid, and comet, their volume would still be insignificant compared to the solar immensity. Before its primordial light illuminated space for the first time, the Sun was born in the chaotic bosom of a collapsing nebula, a vast diffuse cloud of hydrogen and helium, remnant material from previous generations of extinct stars. For eons, this inert cloud moved silently through space. Then a cosmic event triggered its gravitational contraction. Perhaps the expansive shockwave of a distant supernova provided the necessary impulse. Gravity took control, inexorably attracting the gas inward, compressing it with growing intensity. As the cloud contracted, it began to acquire rotational movement, progressively flattening until forming a protoplanetary disk. In the nucleus of this rotational chaos, heat and pressure accumulated until hydrogen atoms were forced to fuse, originating helium through incessant thermonuclear reactions. This ignition instant, the beginning of nuclear fusion, marked the true birth of the Sun. A sudden and brilliant explosion of energy surged outward, igniting a resplendent fire in the heart of the forming solar system. The newly born Sun dispersed the remaining gas and dust with powerful solar winds, thus sculpting the planets and all the celestial bodies that currently orbit around it. But the Sun is much more than a simple sphere of incandescent gas. It represents the gravitational force that governs the dynamics of the entire solar system. Its influence extends along thousands of millions of kilometers, an attraction so formidable that nothing within its vast sphere of dominion can escape. Each planet, each asteroid, each frozen body, even in the most remote confines of the system, obeys its gravitational mandate. If the Sun suddenly disappeared, the entire solar system would disintegrate into incomparable chaos, with its planets launched adrift into the cosmic void. Gravity constitutes the fundamental principle that maintains the solar system cohesive, granting it its structure and its identity as a unified system. The immense solar mass curves space itself, creating an intricate invisible network that maintains all bodies in their designated orbits. This gravitational force explains why Earth requires 365 days to complete its orbit around the Sun, why Mercury, the closest planet, circles it in only 88 Earth days, and why distant Neptune requires the astonishing figure of 165 years for a single orbit. Solar influence is not limited to its gravity. It releases energy constantly, flooding the solar system with vital heat and light. Without this energy, Earth would be a frozen wasteland. Mars would never have had the opportunity to harbor liquid water on its surface, and the outer planets would exist in perpetual darkness. It is a gigantic cosmic furnace that consumes approximately 600 million tons of hydrogen each second through nuclear fusion, a process that will continue uninterruptedly for another 5 billion years. However, the Sun is far from being an immutable and peaceful sphere. Its surface constitutes a boiling sea of plasma in constant agitation and transformation that erupts with immense solar flares and geomagnetic storms. Gigantic loops of charged particles known as prominences extend thousands of kilometers toward space, sometimes collapsing in violent energy-releasing explosions. These storms can launch radiation bursts toward Earth, interrupting satellites, radio signals, and even terrestrial electrical networks. And yet, despite its inherent cosmic fury, the Sun maintains remarkable stability, constant enough to allow life to flourish on Earth, but active enough to remind us of its immense and raw potency. Its light, carrier of vital energy, requires only 8 minutes and 20 seconds to reach Earth, traveling at a speed of 299,334 kilometers per second. This light transports much more than simple heat. It transmits the energy that drives our climate, sustains photosynthesis in plants, and makes possible the existence of life as we know it. Without the Sun, Earth would be a sterile rock adrift in a frigid and desolate silence. Despite all its power and fundamental importance, the Sun is just one more star among the billions that populate our galaxy. Our Sun is located in the outer region of the Milky Way's spiral disk, moving at an astonishing speed of 828,800 kilometers per hour, dragging the entire solar system with it while orbiting the galactic center. In the course of about 230 million years, it will complete a full journey around the center of the galaxy, an odyssey it has performed more than 20 times since its own birth. As we move away from this incandescent giant, we encounter the first world firmly trapped in its relentless gravitational embrace, a small, scorched planet, wrapped in an eternal battle with the incessant heat of the Sun. Our journey takes us to Mercury, the planet closest to the Sun, a world characterized by absolute extremes. It is the smallest planet in the solar system, with a size barely larger than Earth's moon. However, it endures some of the most severe and volatile conditions found on any celestial body in our cosmic neighborhood. Trapped in a delicate and forced orbital dance with the Sun, Mercury is a scorched rock completely devoid of significant atmosphere, mercilessly bombarded by solar radiation and subjected to diurnal temperature changes that defy imagination. Despite being the planet closest to the Sun, Mercury paradoxically is not the hottest. That infamous title belongs to Venus, but this does not diminish Mercury's brutality. During the day, the Sun overwhelmingly dominates its sky, elevating the surface temperature to 427 degrees Celsius, hot enough to melt lead. However, lacking a substantial atmosphere that traps and retains heat, the temperature plummets drastically during the night, falling to minus 179 degrees Celsius, representing an astonishing thermal oscillation of more than 550 degrees in a single planetary rotation. A day on Mercury differs fundamentally from any terrestrial experience. The planet possesses extremely slow rotation, taking 59 Earth days to rotate once on its own axis. But due to its rapid orbit around the Sun, which is completed in only 88 Earth days, a complete cycle of day and night on Mercury extends for an astonishing span of 176 Earth days. Mercury's surface presents an eroded and battered landscape, furrowed by countless craters and steep cliffs, sculpted by billions of years of meteoritic impacts. The planet lacks winds, rain, or significant internal geological activity that could erase the scars of its violent past. One of its most prominent features is the Eris Basin, a gigantic impact crater that measures more than 1,600 kilometers wide, so vast it could encompass a large part of United States territory. Mercury's isolation and its environmentally extreme conditions have made it one of the least directly explored planets. To date, only 2 spacecraft have visited it. NASA's Mariner 10, which performed 3 flybys in the 1970s, and the Messenger probe, which orbited Mercury from 2011 to 2015. Messenger provided us with the most detailed vision of the planet so far, mapping its surface with unprecedented precision and even confirming the presence of polar ice deposits in the permanently shadowed regions of its craters. As we leave behind this small, sun-scorched world, our path leads us toward a planet wrapped in dense golden clouds, an orb even more hostile than Mercury, where heat constitutes a relentless constant and the atmosphere itself is intrinsically poisonous. Before us emerges Venus, the second planet from the Sun, and the most extreme of the inner planets of our solar system. At first glance, it could deceptively appear as Earth's twin, given that it possesses an almost identical size and similar rocky composition. However, beneath its dense, golden-colored clouds lies a world that could not be more radically different from ours. Venus is, in fact, the hottest planet in the entire solar system, with surface temperatures reaching an astonishing 482 degrees Celsius. Unlike Mercury, which experiences drastic nocturnal cooling, Venus never enjoys thermal respite. Its dense atmosphere, composed mainly of carbon dioxide, traps heat in an uncontrolled greenhouse effect, transforming the entirety of the planet into a suffocating and perpetual furnace. This atmosphere is so dense that the pressure on the Venusian surface would be equivalent to that experienced at 1 kilometer depth underwater in Earth's oceans. And the air itself is charged with clouds of concentrated sulfuric acid, making Venus not only extremely hot, but also corrosive and lethal to any known form of life. Venus exhibits another enigmatic characteristic: its rotation. It spins in retrograde direction, that is, backward compared to most planets, which causes the Sun to rise in the west and set in the east in its sky. This rotation is incredibly slow. A single Venusian day lasts 243 Earth days, which is longer than its own year, since it only takes 225 Earth days to complete an orbit around the Sun. Venus lacks large moons, a protective magnetic field, and mobile tectonic plates like Earth's. Instead, its entire surface appears to behave like a single giant and rigid plate, with heat accumulated in the planet's interior occasionally emerging and causing catastrophic events of planetary-scale volcanic resurgence. Lacking tectonic plates that gradually release that accumulated internal heat, Venus could experience long-period excess of relative calm followed by massive volcanic upheavals that completely reconfigure the planetary surface. Despite the infernal conditions on the surface, it has been speculated that life, or at least some analogous microbial form, could subsist in the upper layers of Venus's atmosphere. About 50 kilometers above the surface, temperatures and pressures are surprisingly similar to Earth's, and even small quantities of water vapor have been detected. In 2020, scientists announced the detection of phosphine, a gas that on Earth is predominantly produced by microbes, in Venus's upper atmosphere. This discovery unleashed an intense scientific debate about whether some form of airborne microbial life could exist in the planet's clouds. Venturing deeper into the solar system, we arrive at Earth, a truly unique planet in the known vast cosmos. From space, it reveals itself as a brilliant blue jewel wrapped in layers of swirling white clouds. It has an estimated age of approximately 4,540,000,000 years, having been born from the same primordial cosmic dust that gave origin to the Sun and the other planets of our system. However, unlike its planetary neighbors, Earth evolved until becoming something extraordinary and conducive to life. It is a world composed predominantly of rock and metal. Its internal core, a heart of molten iron in constant movement, generates a powerful magnetic field that acts as a protective shield, deflecting harmful solar particles and cosmic radiation. Its surface in perpetual change is sculpted by vast oceans, dynamic winds, and the tireless activity of moving tectonic plates, fundamental characteristics that have shaped imposing mountains, excavated deep valleys, and given origin to continents that move slowly with geological time. Unlike Venus, whose dense atmosphere suffocates the planet, or Mars, whose air is almost non-existent, Earth's atmosphere constitutes a perfect example of delicate balance. A precise balance of nitrogen and oxygen, creating a thin protective envelope that sustains life and separates it from the cold and desolate vacuum of space. But Earth, despite all its apparent current stability, was in its origins a violent and chaotic world. In its infancy, it was a molten sphere in constant state of solidification, incessantly bombarded by primordial asteroids and comets. For millions of years, its surface gradually cooled, forming a solid and resistant crust. Water, supplied by icy comets that impacted the surface or released from the planetary interior through volcanic activity, accumulated in vast primordial oceans. From the spatial perspective, Earth pulses with incessant movement. Oceans stir with marine currents, clouds transform into endless patterns, and the lights of human civilizations flicker on the planet's dark side, illuminating the night with their activity. It is the only known planet that harbors life, not because it is inherently the only one capable of doing so, but because on this orb conditions aligned in a perfect and singular manner. The habitable zone, that narrow strip around a star where conditions permit the existence of liquid water on the surface, constitutes one of the fundamental reasons why Earth is so exceptionally special. However, location alone does not explain everything. Earth's long-term habitability depends on a complex interconnection of numerous crucial factors: its protective magnetic field, the dynamics of tectonic plates, the balanced composition of its atmosphere, the vast presence of oceans, and perhaps crucially, the existence and stabilizing influence of its moon. Earth's only natural satellite is much more than a mere pretty light eye in the night sky. It plays a crucial and fundamental role in the history and stability of our planet, having formed, according to the main theory, from a colossal impact between young Earth and a Mars-sized protoplanet known as Theia. The Moon's gravitational attraction contributes significantly to stabilizing Earth's axial tilt. Without the Moon, our planet's axis could wobble erratically and wildly, causing catastrophic climate changes that would make life impossible. Leaving behind our home planet, our next destination is our potential future home, the enigmatic red planet, Mars. Mars has been an inexhaustible source of human curiosity for millennia. It is easily visible to the naked eye from Earth, gleaming with a distinctive reddish tone that led ancient civilizations to associate it with war and fire. But the real Mars, the one we have come to know through decades of meticulous robotic missions, is both stranger and more fascinating than any myth or legend. It is a planet of crude extremes, a frozen desert dotted with vast canyons, imposing extinct volcanoes and clear geomorphological signs that liquid water once flowed abundantly across its surface. Nevertheless, Mars today is a predominantly arid, frigid world apparently lacking surface life. A somber reminder of how quickly a planet's destiny can change drastically. Mars orbits the Sun at an average distance of 1.52 astronomical units, which means it is located about 227 million kilometers away, farther than Earth but still relatively close in cosmic terms. It is a planet smaller than Earth, with little more than half its size and only one-third of its gravity. From space, Mars radiates an intense red color, a hue caused by the omnipresent iron oxide-rich dust that covers its surface. This fine powdery layer extends across endless deserts, shaped by fierce winds that can raise planetary-scale dust storms that cover the entire orb for entire months. But Mars is more than a vast expanse of dust. Rising majestically over the landscape stands Olympus Mons, the highest volcano in the entire solar system, rising 3 times higher than Mount Everest. And then there is Valles Marineris, a canyon system so vast that if it were found on Earth, it would extend across the entire continental United States territory. If Earth's Grand Canyon is a prominent geological scar, Valles Marineris is a deep and jagged wound carved into the Martian surface. Despite all its extremes, Mars guards secrets that make it one of the most exciting and promising places for exploration in the solar system. Billions of years ago, Mars was a world radically different from the current one. We possess clear geological evidence that liquid water flowed abundantly there. Long, sinuous riverbeds, dried lake basins, and even what could have been an enormous ocean covering much of the planet's northern hemisphere attest to its aquatic past. Today, water still exists, but predominantly in ice form, confined beneath the surface and in the polar ice caps. And where there was water, could there have been life? That is the great question that drives much of current Martian exploration. Robots like Curiosity and Perseverance have been minutely scrutinizing the planet, searching for chemical and geological signals that life could have existed in Mars's past. Mars's atmosphere constitutes another enigma. It is incredibly thin, composed mainly of carbon dioxide, and offers almost no protection against harmful solar radiation and cosmic rays. Due to the scarce atmosphere that retains heat, surface temperatures oscillate wildly between day and night, warm enough during daylight hours to evoke a false similarity with Earth, only to fall to deadly and relentless cold during the night. Mars possesses two small moons, Phobos and Deimos, irregularly shaped celestial bodies and probably asteroids gravitationally captured by Mars in its past. Phobos, the larger of them, is being slowly attracted toward the planet, and it is predicted that someday it will crash into Mars or disintegrate, forming a thin, ephemeral ring. Deimos, on the other hand, moves lazily in a more distant orbit, a small, solitary rock lost in the vast Martian sky. For centuries, Mars has been the central focus of human curiosity and fascination. It is the most Earth-like planet we have found, and yet so incredibly different in its evolution and current characteristics. It is also, and significantly, the most likely place for humanity to set foot in the near future. Plans for crewed human missions are already actively underway, with NASA, SpaceX, and other space agencies actively investigating and developing ways to send astronauts to Mars in the coming decades. The challenge of such an endeavor will not be insignificant, but if we manage to land there, survive the extreme conditions, and perhaps even build a permanent base, Mars could become the fundamental first step in transforming humanity into a truly multiplanetary species. Mars is also the last of its kind on our journey, the last significant rocky world we encounter in the inner solar system. But before reaching the next planet, we must cross a vast and enigmatic frontier toward a completely different cosmic realm, the asteroid belt. This extensive region is distributed approximately between 2.1 and 3.3 astronomical units from the Sun, which translates to a distance of between 299,595 million kilometers. It is not a homogeneous or unified structure, but rather a chaotic and dispersed ring composed of millions of rocky objects moving in endless and diverse orbits. This belt marks the fundamental dividing line between the inner rocky planets and the gas giants that lie beyond, serving as a distinct boundary between two completely different astrophysical realms within the solar system. Despite its evocative name, the asteroid belt is not a densely populated field of rocks in constant collision, as often portrayed in science fiction. If one were standing on the surface of an asteroid, most likely they would see nothing but the vast and empty surrounding space. The average distance between objects within the belt can be hundreds of thousands of kilometers, making navigation through it much less dangerous than popular representations would suggest. However, it is fundamental to understand that these asteroids are authentic relics of the solar system's infancy, primordial remnants of a planet that never formed due to the immense and constant gravitational pull of nearby Jupiter. The largest and most massive object in this region is Eris, a dwarf planet with a diameter of 950 kilometers that constitutes approximately 40% of the estimated total mass of the asteroid belt. Unlike its rocky neighbors, Eris harbors large quantities of water ice beneath its surface, and recent studies even suggest the possible existence of a briny and muddy subterranean ocean in its depths. If there exists any possibility of life or its components in this frigid region, Eris is the most promising place where it could be hidden. The next bodies in significant size are Vesta, Pallas, and Hygiea, each with diameters reaching ever all 100 kilometers. Vesta is the second largest, with the surface visibly marked by ancient impacts and deep fractures. It is one of the few places in the belt where evidence of past volcanic activity has been detected. Some asteroids like Ida and Dactyl, the latter being its moon, or Eros, are nothing more than rubble piles, collections of loose rocks barely held together by their own weak gravity. Although most asteroids remain in relatively stable orbits within the main belt, some are disturbed by significant gravitational forces, especially by the colossal influence of Jupiter that dominates this region of space. These displaced asteroids, known as near-Earth objects, NEOs, occasionally cross our planet's orbit. Some of them, like the one believed to have caused the mass extinction of dinosaurs 66 million years ago, have drastically altered the course of life on our planet. Today, space agencies meticulously track these wandering asteroids, actively preparing for the possibility, however remote, that one might threaten Earth again in the future. Nevertheless, the asteroid belt also represents a potential stepping stone for humanity's future expansion. Numerous asteroids are notably rich in iron, nickel, and platinum group metals, valuable materials that could someday sustain human expansion into deep space. Some private companies and space agencies have actively considered the viability of mining these asteroids with the goal of extracting water for rocket fuel and using their resources to build future space stations and self-sufficient human colonies. As we move beyond the last scattered fragments of this ancient region, looming before us is the first of the outer planets, a world of such magnitude that it could swallow all the other planets in the solar system and still have room to spare. Now we arrive at Jupiter. This giant planet is an impossible presence to ignore in the solar system. It overwhelmingly dominates the outer solar system, a colossal sphere of swirling gas and violent storms, the undisputed king of planets. If our solar system had a second sun that never fully ignited, it would be this one. Jupiter possesses a mass 318 times greater than Earth's, making it more than twice as massive as all other planets combined. It is a world so immense that its enormous gravity not only shapes the orbits of comets and attracts asteroids, but even influences the orbital dynamics of its planetary neighbors. Without Jupiter's stabilizing presence, the architecture and evolution of our solar system would have developed in a radically different manner. It is located at an average distance of 5.2 astronomical units from the Sun, which translates to approximately 779 million kilometers away. It is a world characterized by turbulent layers of clouds. Jupiter, unlike terrestrial planets, does not possess a discernible solid surface. Instead, it is an extremely dense atmosphere composed primarily of hydrogen, approximately 90% and 10% helium, an elemental composition that surprisingly resembles the Sun itself. At greater depths, the colossal pressure crushes the gas until it transforms into liquid metallic hydrogen, a substance so exotic that it behaves like an electrical conductor, thus generating Jupiter's powerful and extensive magnetic field. Beneath this layer of metallic hydrogen, the existence of a dense core is theorized, although scientists still intensely debate its exact size and chemical composition. Jupiter's most emblematic feature is the Great Red Spot, a colossal and persistent storm that has been active for at least 350 years and possibly much longer. It is a swirling vortex twice the size of Earth, with wind speeds reaching 640 kilometers per hour. A relentless hurricane that has not ceased for centuries. Surrounding the Great Red Spot, Jupiter's atmosphere is furrowed by distinctive colored bands, white, orange, and brown, created by immense jet streams moving in opposite directions at incredible speeds. These bands, called bright zones and dark belts, are composed of ammonia clouds that extend across the entire planet thanks to its extremely rapid rotation. Jupiter rotates faster than any other planet in our system, completing a full day in just 9 hours and 56 minutes. This extremely rapid rotation is the engine of its violent storms, chaotic wind systems, and imposing cloud formations that reach heights of up to 48 kilometers. Beneath these storms lies a vast ocean of metallic hydrogen that encompasses most of the planet's interior. This peculiar metallic liquid is an excellent conductor of electricity, powering a magnetic field 20,000 times more powerful than Earth's. This Jovian magnetic field extends millions of kilometers into space, trapping charged particles and creating an environment of intense and dangerous radiation. Any spacecraft venturing too close to Jupiter runs the existential risk of being fried by radiation of magnitude superior to what would be found in the worst nuclear reactor meltdown. Even Jupiter's own Galilean moons have been marked and affected by this relentless energy. And then there is its colossal gravity. Jupiter's immense mass warps the space around it, attracting comets and asteroids like a gigantic cosmic vacuum cleaner. Historically, it has deflected some dangerous space debris away from Earth, acting as a natural protector, but it has also redirected others toward us, sending some on collision trajectories that have shaped the geological and biological history of our planet. Jupiter's influence extends far beyond its physical size. Its gravity prevented the asteroid belt from agglomerating and forming a cohesive planet, and the gas giant has even captured its own extensive retinue of 95 known moons. Among them, the four largest, Io, Europa, Ganymede, and Callisto, the celebrated Galilean moons, are worlds in their own right, each more fascinating and complex than some planets themselves. Io is the most volcanically active body in the entire solar system, with its surface constantly remodeled by rivers of incandescent sulfur. Europa, for its part, hides a vast subterranean ocean of liquid water beneath its frozen crust, making it one of the most promising places for the search for extraterrestrial life. Ganymede holds the title of the largest moon in the entire solar system, even surpassing Mercury in size, and it is the only known moon that possesses its own dynamically generated internal magnetic field. Callisto, a world of ancient ice heavily cratered, could also harbor a buried ocean in its depths. Moving away from Jupiter, our next destination is Saturn. Saturn is, without doubt, the most dazzling jewel of the solar system, a world wrapped in resplendent golden light, encircled by rings of such vast magnitude that they could extend almost from Earth to the Moon. If Jupiter is the king of planets, Saturn is the elegant ruler, more serene and frigid, but no less powerful in its majesty. It is located at an average distance of 9.5 astronomical units from the Sun, which translates to approximately 1.4226 billion kilometers away. Although it is the second largest planet in the system, it is surprisingly light for its size. If one could place Saturn in a bathtub of sufficiently colossal dimensions to contain it, it would float. This is because it is composed mainly of hydrogen and helium, making it the least dense planet in the entire solar system. Like Jupiter, Saturn does not possess a discernible solid surface, but only endless layers of ammonia and methane clouds that swirl in bands of pale yellow, golden, and creamy tones. But beneath those soft and ethereal colors hides a stormy and dynamic world. Winds on Saturn reach astonishing speeds of up to 1,770 kilometers per hour, almost 3 times the speed of a Category 5 hurricane on Earth. Near the North Pole, an immense hexagonal storm, perfectly formed and of enigmatic symmetry, spans about 32,000 kilometers in diameter. Its strange persistence and geometric shape continue to be objects of fascination and study for scientists. Saturn's deep interior is, in composition and structure, very similar to Jupiter's, with crushing pressures that convert hydrogen into an exotic metallic form that generates a robust magnetic field, although of lesser intensity than its gigantic neighbor. But it is Saturn's rings that, without a doubt, capture most of the prominence and admiration. With an extension of 281,000 kilometers in diameter, but with an astonishing thickness of only about 9 meters, they are composed of a myriad of ice and rock fragments. Some of these fragments are as tiny as grains of sand, while others reach the size of mountains. These rings are not solid, continuous structures, but a vast and complex collection of debris in perpetual motion and orbital reconfiguration, divided into 7 main sections designated alphabetically from A to G. Each section possesses its own unique and distinctive characteristics, intrinsically shaped by the planet's gravity and the constant gravitational pull of its numerous moons. The A and B rings are the brightest and most massive, densely packed with countless pieces of ice that reflect sunlight dazzlingly, conferring Saturn with its iconic majesty. The C ring is fainter and translucent, containing finer particles, which gives it a ghostly, almost transparent appearance. Beyond these main rings, the D ring closest to the planet is so thin and diffuse that it is barely discernible. Moving outward, the E ring is vast and extremely diffuse, formed by the icy plumes and particles that erupt from the moon Enceladus. The F ring, for its part, is a narrow and chaotic band, constantly twisted and remodeled by the gravitational influence of its nearby shepherd moons. Finally, the G ring, the faintest and most distant of all, moves at the limit of Saturn's direct influence, a tenuous whisper of material barely held together. But what is perhaps most fascinating is the Cassini division, that prominent dark and discernible gap between the A and B rings. This division is not completely empty. It still contains scattered particles, but its 4,700-kilometer-wide expanse is largely cleared by gravitational resonance and the pull of the small moon Mimas orbiting nearby. This division, along with many other smaller gaps, demonstrates palpably how Saturn's moons act as true celestial sculptors, modeling and maintaining the delicate balance and complex structure of the rings. These moons, some embedded within the rings themselves, others orbiting just outside them, gravitationally interact with the ice and rock, keeping some areas clear while causing intricate waves and undulations elsewhere. And Saturn has a vast retinue of moons, at least 146 known so far. Some are tiny, barely large enough to be called moons, while others are worlds in their own right. The most famous is Titan, which surprisingly is larger than the planet Mercury and possesses a dense atmosphere. Heir of nitrogen and methane, Titan is the only place in the solar system besides Earth where the existence of liquid lakes and rivers on its surface has been confirmed, although in its case they are composed of liquid methane instead of water. Another moon, Enceladus, hides a vast ocean of liquid water beneath its frozen crust, regularly expelling geysers of water vapor and ice particles into space, making it one of the most promising places for the search for extraterrestrial life in our system. Despite its serene and majestic appearance, Saturn's gravity is a formidable force to reckon with. It exerts an influence derived from a mass 95 times greater than Earth's, firmly keeping its rings, moons, and even influencing the trajectory of distant solar system objects in place. Some asteroids and comets passing through Saturn's gravitational domain are pushed into new orbits, sometimes launched into deep interstellar space, other times redirected to fall toward the inner solar system. As we move away, leaving behind the golden glow and icy rings of Saturn, our route leads us toward a darker, more enigmatic planet still full of secrets to unveil. Next, we arrive at Uranus. Uranus, a truly singular and peculiar world within our solar system. It is located at an average distance of 19.2 astronomical units from the Sun, which places it at almost 2.9 billion kilometers away. It is the seventh planet classified as an ice giant, wrapped in a cold and misty atmosphere that hides its mysteries in its depths. Unlike its more massive and turbulent neighbors, Jupiter and Saturn, Uranus does not radiate with swirling storms or imposing distinctive cloud bands. Instead, it presents itself from a distance as a blue-green sphere of smooth appearance lacking prominent features. Its distinctive color comes from the absorption of red light by methane present in its atmosphere, which allow its blue light to be reflected and dominant. But the most anomalous and peculiar thing about Uranus is not its color, but the way it moves. Unlike almost all other planets that rotate more or less upright on their axis, Uranus is radically tilted sideways, rotating with an axial inclination of approximately 98 degrees. This means that instead of spinning like a vertical top, it literally rolls around the Sun like a ball in a rolling orbit. Astronomers theorize that this strange inclination was caused by a massive collision billions of years ago, possibly with a planet-sized object that toppled Uranus in its formative stages. As a direct result of this extreme inclination, the planet experiences some of the most prolonged and drastic seasons in the entire solar system. For nearly 42 Earth years, one of its poles faces directly toward the Sun, remaining in constant daylight, while the opposite pole plunges into total and prolonged darkness. Then, as Uranus advances in its slow orbit, the situation reverses and the other pole experiences the same extreme cycle. With 4 times Earth's diameter, Uranus is composed mainly of hydrogen, helium, and methane. However, in its deep interior, it is fundamentally different from a gas giant like Jupiter or Saturn. Beneath its atmosphere lies a frozen and muddy interior composed of water, ammonia, and methane surrounding a small rocky core. It is because of this internal composition that Uranus and its neighbor Neptune are classified as ice giants, as they contain a significantly higher proportion of volatile ices than gases in their total mass. And although Uranus appears deceptively tranquil from the outside, it is far from it in its atmosphere. The planet possesses some of the fastest winds in the entire solar system, reaching speeds of up to 900 kilometers per hour. Like Saturn, Uranus also has a ring system, but they are thin, dark, and very faint, almost invisible except under conditions of backlighting by the sun. It also has 27 known moons, many of them named in honor of characters from the works of William Shakespeare and Alexander Pope. The largest, Titania and Oberon, are icy and heavily cratered worlds, while others, like Miranda, exhibit strangely fractured landscapes that hint at violent and geologically active pasts. As we move beyond this tilted and peculiar world, we set our sights on the last of the great planets of the solar system, Neptune. Neptune, the eighth and most distant major planet of our solar system, is located an incredible 30.1 astronomical units from the Sun, which translates to approximately 4.5 billion kilometers away. Neptune is a world wrapped in deep and enigmatic blue mystery. It is a true ice giant, similar in composition and size to Uranus, but of a wilder, more dynamic nature with an atmosphere full of furious storms. Despite being so far from the Sun, where sunlight is 900 times fainter than on Earth, Neptune is far from being a tranquil place. Its intense and deep blue color, notably more vibrant than Uranus's, is due to methane present in its atmosphere, which selectively absorbs red light and efficiently scatters blue. However, this serene appearance is deceptive. Neptune is home to the fastest winds in the entire solar system, reaching impressive speeds of up to 1,930 kilometers per hour. This is faster than the speed of sound in Earth's atmosphere. These supersonic winds lash its dense atmosphere composed mainly of hydrogen, helium, and methane, stirring up massive and persistent storms. The most celebrated of them was the Great Dark Spot, a storm of magnitude similar to Jupiter's Great Red Spot, first observed by Voyager 2 in January 1989. Although the Great Dark Spot subsequently disappeared, other dark storms have formed since then, demonstrating that Neptune's weather is in constant envie. O-length evolution. Beneath those stormy clouds, Neptune's atmosphere gradually thickens until it becomes a hot and dense fluid of water, ammonia, and methane. This supercritical layer, similar to an ice mantle or mud ocean, is comparable to Uranus's internal structure, but Neptune's more intense internal heat could make it more active and dynamic. Even deeper, there is probably a small rocky core of approximately 1 to 2 times Earth's mass, surrounded by a mantle of hot and liquid ices under extreme pressure. Temperatures in Neptune's deep interior could reach 5,000 degrees Celsius, hot enough to melt even rock. That deep interior could harbor one of the strangest and most fascinating phenomena in the solar system, diamond rain. The pressures within Neptune are so intense that carbon atoms could be compressed and transformed into pure diamond crystals that then slowly fall like brilliant rain toward the core. This is not just speculative theory. Laboratory experiments on Earth have managed to recreate the pressure and temperature conditions that could trigger diamond formation in environments similar to Neptune and Uranus. If this theory is confirmed, Neptune's hidden depths could literally be filled with sinking diamonds, adding to the disturbing and majestic beauty of this distant world. Neptune also possesses a system of faint and thin rings, probably composed of dust and ice particles, constantly remodeled by the gravitational interaction of its 14 known moons. The largest of them, Triton, is one of the most singular and strange moons in the entire solar system. It orbits Neptune in retrograde direction, contrary to the planet's rotation, which means it was probably a gravitationally captured object from the Kuiper Belt, a distant region of icy objects beyond Neptune. Triton is also the coldest known body in the solar system, with surface temperatures descending to a frigid 235 degrees Celsius. However, despite this extreme cold, it remains geologically active with geysers of gaseous nitrogen erupting from its frozen surface, a frigid and dynamic spectacle. Neptune itself was the first planet discovered not by direct observation through telescopes, but through the rigorous application of mathematics. In the early 19th century, astronomers noticed that Uranus's orbit did not quite follow predictions based on Newton's laws. Something invisible was gravitationally perturbing it. Using the laws of gravity, astronomers calculated the position of a hidden and unknown planet. And in 1846, Neptune was found with astonishing precision almost exactly where they had predicted it. That discovery demonstrated that the solar system was still full of surprises and mysteries to unveil, even in its most distant and previously unexplored confines. Despite its incredible distance from the Sun, Neptune is not completely isolated from its influence. The solar wind, though weak and very dispersed, still reaches here when it encounters Neptune's magnetosphere. The Sun's gravity also maintains Neptune in an intricate orbital resonance with Pluto. For every 3 orbits Neptune completes, Pluto completes 2, ensuring they never approach dangerously close to each other, despite their orbital paths crossing in certain configurations. Beyond Neptune, the solar system's presence does not cease. It extends into a vast and frozen expanse known as the Kuiper Belt. This is a distant and frigid region, where sunlight appears merely as another bright star in the night sky. It begins approximately at about 30 astronomical units from the Sun, equivalent to 30 times the average distance between Earth and the Sun, and extends to around 55 astronomical units, that is, more than 8 billion kilometers away. Here space is not empty. It is densely populated by countless icy objects coincided primordial relics of the solar system's formation. Some of these objects are tiny, no larger than a common rock, while others reach the size of mountains or even minor moons. Then there are the dwarf planets, the largest and most emblematic objects of this region. For several decades, Pluto was universally considered the 9th planet, a small, solitary, and enigmatic world at the edge of our solar system. However, in 2006, astronomers from the International Astronomical Union made a difficult and controversial decision. They redefined what it means to be a planet, and Pluto, under the new guidelines, did not meet all the established requirements. The fundamental problem did not lie in its size. After all, Mercury is smaller than some moons in the solar system and continues to be classified as a planet. Pluto's crucial problem lay in its orbit. A real planet, by IAU definition, needs to have cleared its orbit of other significant celestial bodies. Pluto does not do this. It shares its orbital trajectory with a multitude of other objects in the Kuiper Belt, which implies that it is just one of many icy worlds that reside in this region. Thus, Pluto was reclassified as a dwarf planet, joining a growing list of similar celestial bodies like Eris and Makemake. Despite having lost its planetary status, Pluto remains one of the most fascinating and geologically complex places in the solar system. Its surface is covered by a mixture of frozen nitrogen, methane, and carbon monoxide, and it possesses a thin atmosphere that collapses and refreezes on the surface as the planet moves away from the Sun in its eccentric orbit. In 2015, NASA's New Horizons spacecraft conducted the first and only close flyby of Pluto, revealing a surprisingly diverse and dynamic landscape, completely different from everything that was expected. Imposing mountains of water ice, vast, smooth plains like Sputnik Planitia, and clear signs of possible subsurface oceans. It is a place where the surface moves and changes, demonstrating that even a world so far from the Sun can continue to be geologically active and alive in its own way. But Pluto is not the only large and intriguing object here. There are other dwarf planets, each with their own mysteries. Haumea is one of the strangest and most anomalous objects in the Kuiper Belt. It rotates so rapidly on its axis that it has stretched to acquire an elongated, almost elliptical shape, similar to that of an egg. Furthermore, it has been discovered to possess a ring system, making it one of the few known ringed objects beyond the gas giants. Then there is Makemake, whose surface is covered with frozen methane, giving it a distinctive reddish hue. Its surface is so frigid that even gases like nitrogen and methane freeze and precipitate, forming a thin and irregular layer of ice. But these are only the most prominent and studied names. The Kuiper Belt is filled with thousands, perhaps even millions of smaller icy objects that have mostly never been explored up close. Some of these bodies may be tiny, simple pieces of frozen rock, but others could be undiscovered dwarf planets waiting patiently in the vast outer darkness. Many of these objects follow strange, elongated and highly inclined orbits, shaped by the gravitational influence of Neptune and possibly even by an invisible planet lurking much farther beyond the Kuiper Belt, which some astronomers hypothesize as Planet 9, a massive world that could be hidden in the depths. The Kuiper Belt is also the main source of many short-period comets, those that orbit the Sun in less than 200 years. Occasionally, Neptune's gravity gravitationally perturbs one of these icy bodies, sending it on a forced journey toward the inner solar system. When that occurs, the progressive heat of the Sun causes the comet's icy material to sublimate and vaporize, creating the brilliant and spectacular luminous tails that we observe from Earth. One of the most famous and D-periodic comets, Halley's Comet, is believed to originate from this region, but the Kuiper Belt does not represent the final limit of the solar system. As we move away from it, objects disperse even more, entering a chaotic cosmic region known as the scattered disk. The scattered disk is the vast region where the solar system, in its most extended definition, begins to gradually dissolve into interstellar space. If the planets and the Kuiper Belt represent the well-maintained and orderly garden near a house, the scattered disk would be the overgrown and disorderly field at the farthest end of the cosmic property. It is a wild and unpredictable place where gravitational interaction and chance have left objects stranded in extremely erratic orbits. It extends from the outer edge of the Kuiper Belt, approximately 30 astronomical units from the Sun, and projects much farther, to at least 1,000 astronomical units away. Although the exact limit is not clearly defined, unlike the relatively stable objects of the Kuiper Belt, the scattered disk harbors icy bodies with markedly extreme orbits. Some are inclined at sharp angles relative to the solar system plane, while others stretch in long elliptical trajectories that take them considerable distances from the Sun before returning closer. These objects did not intrinsically form with such orbits. They were once constituent parts of the Kuiper Belt. However, long ago, Neptune's immense gravity violently perturbed them, launching them into these eccentric and unpredictable trajectories. One of the most famous and significant objects of the scattered disk is Eris, a dwarf planet that, although slightly smaller than Pluto, is considerably more massive. It orbits the Sun at an average distance of 68 astronomical units, but its trajectory is highly elongated, taking it up to 97 astronomical units at its aphelion and as close as 38 astronomical units at its perihelion. To contextualize these distances, remember that 1 astronomical unit is the average distance between Earth and the Sun, approximately 150 million kilometers. This means that Eris, even at its closest point to the Sun, is almost 40 times farther from our star than Earth, and at its farthest point is found almost 100 times that distance, making it one of the most remote known objects in our solar system. Its orbit is also inclined about 44 degrees compared to the main solar system plane, an unmistakable sign that it was violently launched to that position by Neptune's gravitational influence eons ago. In 2005, when Eris was first discovered, it was initially thought to be larger than Pluto, which unleashed the fundamental debate that eventually led to Pluto's reclassification as a dwarf planet. Eris is not alone in this realm of scattered orbits. There are many other known scattered disk objects, including Gong-Gong, Sedna, and 2007 OR10, some of which could also be classified as dwarf planets. Most of these objects have never been observed closely by a space probe. We only know them as small points of light in astronomical images, their surfaces and compositions completely unknown. However, we know they are among the reddest objects in the entire solar system, suggesting they are probably covered with complex organic molecules formed by intense cosmic radiation that bombards their icy surfaces over eons. The scattered disk differs from the Kuiper Belt in a fundamental way. It is not really a belt in the sense of a relatively flat band of objects. While the Kuiper Belt is a more or less flat region that follows the same general orbital plane as the planets, the scattered disk extends in all three-dimensional directions. Some of its objects have orbits that extend significantly above or below the solar system plane, inclined at extreme angles. This suggests that these objects were not just gently pushed by Neptune but were violently thrown into their current orbits through dramatic gravitational encounters. In fact, some of them may have been sent so far that they integrated into the next outer region. One of the most intriguing objects of the scattered disk is Sedna, a reddish-toned world that never approaches closer than 76 astronomical units from the Sun and moves away to an astonishing distance of 937 astronomical units, far beyond the direct reach of Neptune's gravity. Its extremely elliptical orbit takes approximately 11,400 years to complete, which means it was last in its current position when humans were still painting on prehistoric cave walls. The reason for Sedna's strange orbit is a persistent scientific mystery. Some scientists believe it was dragged into its current trajectory by the close passage of a different star during our Sun's early infancy. Others theorize that it could have been gravitationally influenced by an invisible and massive planet lurking much farther beyond Neptune. This hypothetical object, some astronomers refer to as Planet 9, a yet-to-be-discovered world hidden in the cosmic darkness. Much farther beyond the scattered disk and the last known dwarf planets and the discernible reach of Neptune's gravitational influence, the solar system begins to gradually dissolve into the vast and silent void of interstellar space. However, this end is not abrupt. Instead, it fades gently into a distant and invisible spherical layer of icy objects, a place so remote from the Sun that even its powerful gravity barely manages to retain them. This is the Oort Cloud, a vast and mysterious region believed to represent the true and final frontier of our solar system. The Oort Cloud differs radically from everything we have encountered so far in our journey. It is not a flat disk like the Kuiper Belt, nor a chaotic dispersion of ice and rock like the scattered disk. On the contrary, it forms an immense and diffuse sphere that envelops the Sun from all directions, extending from around 2,000 astronomical units to an astonishing distance of 100,000 astronomical units. This implies that the outer edge of the Oort Cloud could be about 15 trillion kilometers away. To put it in perspective, sunlight would take more than a year to travel and reach the outermost edge of the Oort Cloud. Unlike the inner solar system, where planets and asteroids orbit in relatively orderly and predictable trajectories, objects in the Oort Cloud are scattered in all directions, moving with extreme slowness in the profound darkness of space. To date, no spacecraft has traveled far enough to directly observe these objects. In fact, we have never directly observed an object confirmed to originate from the Oort Cloud. We only infer its existence due to the appearance of long-period comets, icy bodies that occasionally fall slowly toward the Sun from extreme distances before returning to the unknown. Some of these comets take thousands or even millions of years to complete a single orbit, suggesting an origin much farther beyond the Kuiper Belt or the scattered disk. Scientists theorize that the Oort Cloud is composed of trillions of icy bodies, considered primordial relics of the solar system's formation. It is plausible that these objects were born much closer to the Sun, within the same rotating disk of dust and gas that gave rise to the planets. But in the early and chaotic days of the solar system, they were violently expelled outward by the immense gravity of Jupiter and the other giant planets, being launched so far that they settled in this vast and distant spherical layer. Some of these icy bodies might even have had an extrasolar origin, having been captured by the Sun's gravity. Billions of years ago, one of the greatest mysteries of the Oort Cloud is its precise extent. Its inner edge at about 2,000 astronomical units, approximately 299,000 million kilometers, is still weakly gravitationally bound to the Sun. But at its outermost limits, around 100,000 astronomical units, 15 trillion kilometers, the Sun's gravity is barely perceptible, being overcome or at least as strong as the attraction of nearby passing stars or the weak gravitational pull of the Milky Way itself. Some scientists even suspect that a second layer of even more distant icy bodies might exist, called the Hills Cloud, which would further extend the theoretical reach of the solar system. Long-period comets are our best indirect evidence for the existence of the Oort Cloud. When a distant object from the Oort Cloud is perturbed, perhaps by the gravitational attraction of a passing star, it can begin a slow spiral fall toward the inner solar system. As it approaches the Sun, its icy surface begins to sublimate and vaporize, releasing gas and dust and thus forming the brilliant and spectacular tails that characterize comets. Perhaps the most fascinating question about the Oort Cloud is whether it harbors worlds yet to be discovered. Most of its objects are small, only a few kilometers in diameter. But some scientists postulate that there could be much larger bodies hidden in its depths. Perhaps even a Mars-sized planet that was expelled from the planetary region long ago and now drifts through the frigid and lonely darkness, frozen and forgotten by most of the cosmos. If such an object exists, it would be incredibly difficult, almost impossible to detect with current technology, as it would reflect an insignificant amount of sunlight and would take thousands of years to complete a single orbit. By crossing the Oort Cloud, we leave behind the last icy remnants of the direct and discernible material H of the solar system. Here, beyond the scattered comets and frozen debris, the Sun is no longer the principal architect of all orbital movement. Its light is now simply that of another distant star, no brighter than many others in the vast cosmic ocean. But while its gravity can still weakly cling to the outermost objects of this realm, there is another force at play, a different type of cosmic boundary, one that is not defined by physical matter, but by the invisible and energetic breath of the Sun itself. This is the Heliosphere, the great protective bubble that shields the solar system from the true immensity and potentially hostile forces of interstellar space. The Heliosphere is shaped by the solar wind, a constant stream of charged particles, mainly protons and electrons, that rush outward from the Sun at astonishing speeds of up to 1,450,000 pound-kilometers. These particles exert dynamic pressure against the interstellar medium, the extremely tenuous plasma and cosmic radiation that moves between stars, forming a huge protective bubble around the solar system. Although invisible to the naked eye, the heliosphere is essentially a vast cosmic force field, a vital shield that deflects harmful high-energy galactic cosmic rays and keeps the internal environment of our solar system relatively stable and protected. Without its existence, Earth and all other inner worlds would be constantly bombarded by high-energy particles that could strip planetary atmospheres and wreak havoc on any form of life. As we move toward the outer solar system, the speed and density of the solar wind begin to decrease noticeably. The first significant boundary we encounter in this direction is the termination shock located somewhere between 80 and 100 astronomical units from the Sun, which translates to a distance of between 11,900 to 15,000 million kilometers. Here, the solar wind, which once moved at supersonic speeds, suddenly drops to subsonic levels as it collides with the slower and denser interstellar medium. The result is a region of intense turbulence and agitation, a chaotic and stormy area where solar particles collide and mix violently with incoming galactic material. Beyond the termination shock lies the heliosheath, a vast, still unstable region that extends tens of billions of kilometers outward. Here is where the solar wind struggles to maintain its coherence and pressure, diminishing even further as it encounters the increasing pressure of the surrounding interstellar space. It is an area characterized by shifting currents, complex magnetic interactions, and swirling particle flows, representing a final and dynamic battlefield between the Sun's direct influence and the immensity beyond its bubble. Then, finally, we arrive at the Heliopause. This is the true boundary of our solar system's magnetic and particle influence. It is the exact place where the force and pressure of the solar wind are ultimately overcome by the forces of interstellar space. Located at about 120 astronomical units from the Sun, which equals approximately 17,700 million kilometers distance. The Heliopause is the sharp interface between two distinct cosmic domains, the protective bubble generated by the Sun and the raw, unfiltered, and hostile environment of the galaxy. Beyond this point, the solar wind ceases completely. What is found is the pure and unaltered interstellar medium, a vast canvas beige. Irradiation from distant supernovas and other high-energy cosmic events moves freely. The precise shape of the heliosphere remains an object of ongoing scientific debate and modeling. Some theoretical models suggest it is almost spherical, while others propose it is elongated like a comet with a long tail of solar material extending far beyond the solar system. This heliotail, if it exists, could extend for hundreds or even thousands of astronomical units, gradually mixing with the surrounding interstellar medium. As the Sun moves through the galaxy in its orbit, the heliosphere may dynamically change shape, expanding or contracting according to the density and properties of the interstellar material it encounters on its path. Only a handful of human-built objects have ventured so far. The Voyager 1 and Voyager 2 probes, launched in 1977, have managed to cross the Heliopause, officially entering interstellar space. Voyager 1 achieved this in 2012, followed by Voyager 2 in January 2018. However, even here, in the cold and desolate vacuum beyond the Sun's direct influence, these pioneering spacecraft are barely at the beginning of their galactic journey. Moving at their current speeds, approximately 61,000 km for Voyager 1 and 55,000 km for Voyager 2, it will take them more than 40,000 years to reach the vicinity of another stellar system. They are alone, drifting in the endless night of space, carrying with them gold-plated records with recordings of human culture as time capsules destined for any intelligent life form that might someday encounter them. The Voyager probes were meticulously constructed for an ambitious mission to explore the outer planets of our solar system, revealing worlds we had never observed up close with such level of detail. They far exceeded their original objective, providing stunning images and crucial data that drastically reshaped our understanding of Jupiter, Saturn, Uranus, and Neptune. However, their extraordinary journey did not culminate there. Unlike other spacecraft that eventually fall back toward the Sun or crash into their target planets, the Voyagers were provided with the speed and trajectory necessary to completely escape our solar system's gravitational pull. Now these ingenious human creations are on a journey of no return toward interstellar space, destined never to return. Each probe weighs around 720 kg and is approximately the size of a small car, about 3.6 meters in diameter, not including its antenna or instrument arms. The most distinctive feature of each probe is its 3.6-meter high-gain antenna, which remains precisely pointed toward Earth, sending data at an astonishingly slow rate of 160 bits per second, much slower even than the first dial-up internet connections. A trio of radioisotope thermoelectric generators, RTGs, provides the necessary energy for their operation, powered by the decay of plutonium-238. However, the output power of these generators decreases inexorably with time as the plutonium radioactively decays. It is estimated that by the mid-2030s, both Voyager probes will be silenced forever, unable to communicate with Earth. The probes were originally equipped with 10 scientific instruments, including imaging cameras, now turned off to conserve energy, magnetometers, plasma sensors, and cosmic ray detectors. These instruments were crucial for mapping Jupiter's massive radiation belts, discovering the complex atmospheres of Saturn's moons, and, most importantly, for their extended mission, detecting and studying the edge of the heliosphere, the bubble-shaped region dominated by the Sun's particle and magnetic field influence. In 2012, Voyager 1 officially crossed the Heliopause, the outermost region and boundary of the heliosphere. The probe detected a dramatic drop in solar particle density and a strong increase in cosmic ray intensity from deep space, unequivocally confirming its escape from the solar system and entry into interstellar space. 6 years later, Voyager 2 followed, crossing into true interstellar space in 2018, providing additional data that confirmed and expanded Voyager 1's findings, offering an unprecedented view of the transition zone between our system and the galaxy. But beyond their valuable scientific instruments, the Voyager probes carry something even more unique: the golden records. Each probe is equipped with a gold-plated copper phonograph record, an ingenious time capsule of human civilization on Earth. The discs contain 115 encoded images of life on Earth, ranging from human anatomy and biological diversity to natural and urban landscapes, along with a selection of natural sounds such as ocean waves, wind, and animal calls. Also included are greetings in 55 different languages, as well as a carefully curated selection of music spanning diverse cultures and historical periods, from Baroque compositions by Bach to the revolutionary rhythm of Johnny B. Good by Chuck Berry. These disks are protected by aluminum covers with clear diagrammatic instructions on how to play them and a symbolic map showing Earth's location in the Milky Way. The underlying idea was that if an intelligent alien civilization ever encountered these millennial probes, they would have a fundamental vision and introduction to the life and culture of the world that created them. Carl Sagan, who led the disk project, poetical. He described them as a bottle thrown into the cosmic ocean, a small hope for communication across vast distances and eons. The Voyager probes continue their inexorable advance outward, but toward where exactly they are heading in the immense galactic canvas remains uncertain. At their current speeds, approximately 61,000 km for Voyager 1 and 55,000 km for Voyager 2, they are destined to wander the galaxy for millions of years without any particular stellar destination in mind. In approximately 40,000 years, Voyager 1 will pass within 1.6 light-years of Gliese 445, a small red dwarf in the constellation Camelopardalis. Meanwhile, Voyager 2 will approach within 1.7 light-years of another red dwarf, Ross 248, in the constellation Andromeda, not to be confused with the galaxy, in about 42,000 years. These stars, however, are still too distant for the probes to approach them significantly, much less enter their planetary systems to explore them. If nothing cosmic collides with them, the Voyagers will continue drifting endlessly in vast interstellar space long after Earth itself has changed beyond recognition. To put their journey in broader perspective, consider this. Even at their tremendous speeds, it would take them more than 17,000 years to travel the distance of just 1 light-year. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away, an unfathomable distance by human scales. If Voyager 1 were heading directly toward it, which is not the case in its current trajectory, it would take more than 70,000 years to arrive. Despite being so far from home, the Voyager probes continue to provide invaluable science. They have confirmed the existence and properties of the interstellar medium, the space between stars, which is composed of a low-density plasma of charged particles and magnetic fields. They continue to detect cosmic rays, study interstellar magnetic fields, and analyze the winds that blow between stars, thus helping scientists understand the composition and dynamics of what lies beyond the direct influence of our Sun. The data they send to Earth is invaluable, but time is inexorably running out for these pioneering machines. By the mid-2020s, NASA will begin the process of shutting down their remaining scientific instruments one by one to conserve the dwindling energy generated by their RTGs. It is estimated that by 2036, both spacecraft will likely be silent forever, drifting inertly in the cold, silent darkness of the cosmos. At this stage of their odyssey, the Voyager probes are no longer simply part of the solar system. They are wanderers at the interstellar boundary, silent ambassadors, small machines drifting in the abysmal void, carrying Earth's fundamental history and humanity toward eternity. They are no longer gravitationally bound to any world, no longer part of any particular stellar system. Now their destiny is to belong to the stars themselves, navigating toward the unknown without the ability to look back. And here we find ourselves, beyond the reach of our Sun's direct influence, immersed in the vast and endless ocean of interstellar space. In this realm, no known planets orbit. There are no moons casting familiar shadows or rings dispersing light in recognizable patterns. The gravitational and energetic forces that shaped and govern our solar system are now distant memories diluted by the immensity and cosmic scales. This is interstellar space, the great expanse between stellar systems, where our Sun's influence fades and the universe itself takes control, revealing its most fundamental properties. But interstellar space is not merely a vacuum. It is a place of subtle and invisible forces shaped by the same large-scale cosmic processes that gave rise to galaxies, stars, and ultimately everything we know. It is filled with a tenuous and ghostly substance known as the interstellar medium, ISM, a vast and diffuse collection of gas, dust, and cosmic rays that extends ubiquitously between stellar systems. This medium is incredibly sparse compared to the air we breathe on Earth. In the densest regions of the ISM, one might find barely a few atoms per cubic centimeter. If we compare this to Earth's atmosphere, which contains approximately 10,000 trillion molecules per cubic centimeter at sea level. Interstellar space seems almost like a perfect vacuum. However, even these faint traces of matter contain the primordial and raw ingredients necessary for the formation of future stars and planetary systems. The interstellar medium is not uniform in its composition and properties. It varies drastically in density, temperature, and chemical composition according to location in the galaxy. Some regions are vast voids, filled only with diffuse wisps of hydrogen and helium that drift slowly for millions of years. Others, in contrast, are dense molecular clouds of gas and dust, the cosmic incubators where new stars are slowly taking shape through gravitational collapse. Certain areas are bathed in intense radiation, lashed by the powerful winds of dying massive stars, while others remain calm and apparently undisturbed. Over time, all this medium is in dynamic motion, stirred by the differential rotation of the galaxy and the chaotic interactions of gravity, gas pressure, and complex magnetic fields. One of the key characteristics of interstellar space is its vast galactic magnetic field. Unlike the magnetic fields of individual planets or stars that are generated by rotating molten cores or internal plasma flows, the galaxy's magnetic field is woven through the interstellar medium itself on a gigantic scale. These magnetic fields are extremely weak, millions of times weaker than Earth's magnetic field, but they play a crucial role in how ionized interstellar gas and charged particles move. They guide the flow of energetic particles, influence the formation of large-scale cosmic structures, like the spiral arms of galaxies, and even help direct the trajectories of high-energy cosmic rays that travel throughout the galaxy. Cosmic rays, one of the most mysterious and energetic forces in interstellar space, are high-energy subatomic particles, mainly protons and bare atomic nuclei that move through space at speeds close to the speed of light. Some of these cosmic rays originate from violent explosions of nearby supernovae, while others come from distant galaxies harboring highly active supermassive black holes. These particles constantly bombard interstellar space, colliding with atoms in the medium, ionizing gas, and affecting the complex chemistry of space itself. Despite their incredible speed and energy, they are often deflected and slowed by galactic magnetic fields, bouncing through space in unpredictable ways before losing energy and settling into the denser interstellar medium. Interstellar space also carries shock waves generated by ancient and ongoing cosmic events. When a massive star dies in a supernova explosion, it sends a colossal burst of energy and matter that can ripple through the interstellar medium for thousands of years, compressing existing gas clouds, heating dust, and crucially, even triggering the birth of new stars in previously stable regions. These shock waves, moving at thousands of kilometers per second, shape the large-scale structure of the galaxy itself, pushing and pulling matter into vast networks of filaments and cosmic voids. More than simple empty space, the interstellar medium is a fundamental dynamic force that drives stellar and galactic evolution over eons. Over millions of years, clouds of gas and dust, upon accumulating sufficient mass, can collapse under their own gravity, forming new stars and with them new planetary systems. In a sense, interstellar space is the galaxy's womb, the place where stars are born and eventually to where they return after dying, dispersing their newly synthesized elements into the medium. The heavier elements created in previous generations of stars, such as carbon, oxygen, nitrogen, iron, among many others, are dispersed into the interstellar medium, mixing with younger gas clouds and thus seeding the next generation of stellar formation with the ingredients necessary for life. The temperature in interstellar space varies drastically. Some regions, particularly near young and hot stars or in supernova remnants, can reach temperatures of thousands or even millions of degrees Celsius. But most of interstellar space is extremely cold, maintaining itself barely above absolute zero at about 271 degrees Celsius. In these frigid and low-density conditions, complex molecules, including organic ones, can form on the surfaces of tiny dust grains, slowly growing into increasingly elaborate prebiotic compounds. Some scientists theorize that the fundamental building blocks of life itself, such as amino acids, water molecules, and other complex organic materials, may have first formed in interstellar space, drifting for millions of years before being delivered to forming planets, including the young Earth. The scale of interstellar space is almost impossible to comprehend intuitively for the human mind. While distances within our solar system are conveniently measured in astronomical units, AU, that is, the average distance between Earth and the Sun, interstellar distances are measured in light years. A light year represents the distance that light travels in one Earth year, which equals about 9.46 trillion kilometers. The stellar system closest to our Sun, Alpha Centauri, is 4.24 light-years away, which translates to approximately 40 trillion kilometers, an unfathomable distance in our daily experience. Even moving at the speed of the fastest spacecraft we have built, it would take tens of thousands of years to reach it. And yet, interstellar space is much more than the simple, empty distance between stars. It is the cosmic boundary, the fundamental threshold between the domain of one star and that of the next. Our Sun's influence, though still present at its outermost confines, has faded in this vast realm. But ahead lies the gravitational reach of another star or stellar system like Alpha Centauri, our nearest neighbor. Here is where the cosmic reign of one star ends and that of another begins. The interstellar medium extends between them like an invisible thread, connecting all stars in the vast and majestic Milky Way galaxy, which in turn is only one among billions in the observable universe. Our solar system, Alpha Centauri, and all the other stars we see shining in the night exist within this greater galactic structure, a spiral galaxy spanning more than 100,000 light-years in diameter, filled with stars, nebulae, and an incalculable number of planetary systems yet to be explored and discovered,